Hello and welcome back to the second video in the Network Defense series. In this video we'll explore more traditional defensive measures. The traditional approach to network defense is the stronghold approach, where the typical metaphor is the medieval castle with high and thick walls, a moat around it, and a drawbridge as a single point of entry that could easily be defended. And as we'll start seeing, in terms of network architecture and the devices that we use to defend an infrastructure like that, that metaphor is actually spot on. So in the previous section, when we talked about networks and network architectures, we talked about the router as the device that connects multiple local area networks together, and that the function of the router is to make packets move. That is absolutely correct. However, there are also situations in which we don't want packets to move, and at that point we need to have some form of a control mechanism, and that primary control mechanism that many organizations rely on is the firewall. You can think of the firewall as the drawbridge. That's the one way in and the one way out of the castle. And if you want to leave the castle or go in, you have to go through the firewall. And the sentries will only let you in if they know who you are and if they believe that you have valid business there. That's the job of the firewall. That means that for a firewall to be effective, it needs to know what kind of network traffic should be allowed in and out of the network. Now, the router itself just knows about IP packets. It doesn't know anything about TCP in most cases, or even higher level protocols like HTTP or DNS or any of that stuff. And so the router itself is, in its purest form at least, not aware of the transport layer protocol or anything above. It just sees it as payload, and because it sees it as payload, it can't easily filter on that. That's where the firewall comes in. So first off, it's important to realize that the firewall has two roles, not just one. Yes, the role of the firewall is to block unwanted traffic and to let wanted traffic through, and as such it functions as a single point of control between untrusted networks, or at least networks of different trust levels. But the second role of the firewall is also to create a second point of visibility, and that's visibility into network traffic coming into the organization, but also visibility into network traffic that would be leaving the organization. So these two roles of the firewall are important, and those are the foundations on which many current security models are being based: the single point of control and the single point of visibility. Traditional firewalls operate at the network layer, so they can specify access in terms of IP addresses, but they can also specify access in terms of transport layer. So they are aware of TCP, UDP, and whatever other protocols live at the transport layer. Modern firewalls are also stateful, and that means that they are aware of what TCP protocols should look like. And for example, we know from a three-way handshake that we want to initiate a TCP connection. We start by sending a packet that has the SYN flag set. The receiving host, the server, will respond to that with SYN and ACK, and from that point on, the ACK flag will be set. The firewall knows that too, so if it sees things like SYN-ACK come in without it having seen a SYN packet, the firewall is able to block that traffic because it shouldn't have been there in the first place. That's called stateful. It's aware of the state of the TCP handshake and the connection that goes through it. But most firewalls, traditional firewalls at least, are not aware of higher level protocols. They don't know HTTP from FTP from SMTP. For them, that's all just data and payload. And so that means that if we're going to define access, we have to do it in terms of IP addresses, transport layer protocols, and port numbers if appropriate. One of the key things to keep in mind is that the firewall is not a router. The firewall's primary task is to stop traffic. The router's primary task is to enable network traffic's movement. In practice, most devices will combine a lot of the functionality into one device, but purely from a functional perspective, they are very different functions. Now, I started by saying that current firewalls don't necessarily know much about the data that's going through them, as long as that's data that lives at protocol levels, I should say, above the transport layer. Next generation firewalls, or application-aware firewalls, as they are also known, are able to do that. And that means that they can do everything that a traditional firewall can do, but they can also now go into more detail. So for example, I can specify in a firewall configuration, an application-aware firewalls configuration, that I only want, say, TLS traffic going to TCP port 443. And that means that the firewall is smart enough to inspect that traffic, see if it matches the fingerprint of TLS, and if it does not, block that. And so let's take a look at the example here, that same exact example. So let's assume that we are tasked with implementing network defense mechanisms to protect network traffic going to a TLS-enabled web server. And that web server will have IP address 10.1.2.3. Now, a web server, TLS-enabled, typically listens on TCP port 443. It could listen on any port, but for now the standard port is 443. So if we want to do this regulating of access using a router, all we could say is, well, we can have network traffic coming from anywhere to TCP, to IP address 10.1.2.3, the end. Because the router doesn't know about anything else. The router doesn't know about TCP or HTTP or ports or any of that stuff. And that would basically mean that we have to open up all services on that server if the router was the level at which we filter. We don't want that. We want to have more granular control over our configuration. So in comes the firewall. The router is going to make sure that the traffic gets to the destination. The firewall is going to now limit it to only that traffic that should be there. So the firewall could, for example, regulate traffic from anywhere, again, to TCP port 443 on IP address 10.1.2.3. But it still wouldn't know that it should only allow through TLS traffic. For example, if someone would be able to compromise that server and disable the web server, they could easily stand up a quick netcat listener to exfiltrate non-TLS traffic from there, and the firewall would be more than happy. The firewall would see, well, this is traffic going to TCP port 443 on this IP address. That's allowed. Nothing wrong here. Carry on. Yet that's not the desired behavior that we're looking for. Those next generation firewalls, or the application-aware firewalls, would be able to catch this, because now we would be able to specify, let's allow traffic from anywhere, as long as at the transport layer it's using TCP. That traffic is going to TCP port 443 on IP address 10.1.2.3, and the application layer protocol should be TLS. Now, that's as good as we can get using firewalls at the moment, because we don't know what's in that TLS. TLS is encrypted, so it could be something else. But, this is as close as we can get for now. So that's the next generation firewalls. Those are rapidly gaining popularity, but not all organizations have them in place yet, for a number of reasons. One is price, although that's coming down. But two, it also requires expertise that most traditional firewall administrators have not been trained in. So they need to be retrained before they can redo these rule bases. It's coming. It's something that's unavoidable, but we're not there yet. Now, if we want to know what's inside that TLS traffic, we have to, at some point, figure out how to break that open. And of course, the whole point of TLS is that you cannot do that. There are ways to do it, though, and that's by using a proxy. Proxies are useful, but they function similar to firewalls, however not the same. If I'm routing traffic through a firewall, the firewall looks at the traffic and makes an access decision based on that. The network traffic itself is not changed though by the firewall. We're not touching anything. A proxy, it's different. So let's take a look at the image here on the slide. On the left hand side we see, say, the internet, and we are using a, in this case, reverse proxy connection to terminate our proxy on this device over here, the proxy device. And between our host on the internet and our proxy, we're using the HTTPS protocol. So it's all encrypted, the internet is secure. No, our connection on the internet is secure. But this is where the connection ends. And at this point what we're doing is really creating a new connection from the proxy to the server, but that goes over HTTP. And the server responds back over HTTP to the proxy. And at that point the proxy will be able to re-encrypt and send an HTTPS response. Of course, the benefit is that at this point we're looking at HTTP, it's all plain text, and that means the IDS can inspect it. This is not necessarily the recommended setup at the moment. We really don't like this unauthenticated traffic because that's the side effect of not using HTTPS, but sometimes it's just what we have to do. To configure routers and firewalls and all of those filtering countermeasures, we somehow have to specify the policy by which they have to adhere. And that is commonly referred to as an access control list, an ACL or an ACL, and they're all the same things. So those are defined by network administrators or security administrators, and they describe what traffic is allowed through the device and which traffic is not. Those ACLs typically consist of a sequence of rules. Each rule is a condition and a consequence, and the idea is if the packet that's being inspected matches the criteria set out in the condition, then the consequence is applied. So for example, if we're saying if the destination IP address is 10.1.2.3, then the traffic is allowed through. So the condition is, does the IP address, the destination IP address match? And the consequence is, yes, you're allowed through. The typical approach to this is that ACLs are processed in order from top to bottom, and that processing stops as soon as the first rule matches. It also means that if no rule matched, that we have to figure out what to do then, and that typically would be a default action that is listed last, and depending on your circumstances, you might want to end up with a default deny or a default permit. Default permits are more rare than default denies though. They can typically incorporate all kinds of conditions. It depends on the device. If you're dealing with a router, only IP addresses. If you're dealing with a firewall, IP addresses, transport layer protocols, and port numbers. And if you're dealing with an application-aware device, you might even be able to describe what protocols are being used. And as mentioned, a good ACL should always end with a default posture, a default deny in most cases. So this is not an exact syntax in use by any devices today, but they look very similar to this. So if I would, for example, be filtering out in a traditional firewall, I might say permit, so that would be my consequence. TCP, that would be the part of the condition. Any would be the source host. The 192.168.42.16 would be the destination host. And EQ stored for equal 80. So this would be a permit rule that allows any source to connect to IP address 192.168.42.16 as long as they're using TCP destined to port 8080. In the next generation firewall, I might be a little bit more complete. I might, for example, describe that we're not just permitting TCP, but we're permitting HTTP from anywhere to that IP address and that port number. And at this point, we have a subtle but very important difference. And the difference, of course, is that TCP in the firewall rule up here has been replaced with HTTP down here, where this would be a transport layer protocol and this would be an application layer protocol. So a subtle distinction, but an important one. And then down here, of course, we have our default denies. So deny TCP any equal 80 log. So in other words, if anyone is trying to connect to my web server on any system, TCP 80 log it. Now this is any system except those systems that were listed in firewall rules above this, and of course anything else I want to log as well. And so it's the job of a firewall administrator to really work through these firewall rules and specify those policies. Let's look at another example. So for example, here I have two permits and one deny rule. The first permit will allow TCP traffic coming from anywhere to that IP address 192.168.42.80 equal www. That's a symbolic notation for TCP port 80. And we'll have a permit TCP any equal SMTP, which is symbolic for TCP port 25. Anything else, any other traffic, as long as it's IP traffic, is being denied. And so as we analyze and pick apart this rule, we might be able to see that since it is a traditional firewall, if I can somehow not run a standard web server on this port 80, I might be able to run my own backdoor on there. And so we have to be very careful with how we specify these rules. Firewalls and proxies are preventative controls because they regulate what traffic can go through and what cannot. But since network traffic is transient, and that means it's only there when it's being passed through the system, when it's on the wire, we can't see it after it happens because it's gone, it's no longer there. It's like looking at a road and trying to figure out what cars passed by 10 minutes ago. It doesn't work that way. And that means that we need to have some form of logging going on. That means that we need to keep records of what packets go over our network, or maybe what cars pass through the toll booth. Otherwise we can't send them a bill. If we do that on the network equivalent, we call it network security monitoring, or NSM. And the idea is that we configure all of those devices to generate the logs that we think we might need down the road, either in terms of operational troubleshooting or in terms of security posture, or maybe billing. It depends on what your use case scenario is. For a security perspective, what we have to keep in mind is that a lot of the important logging, at the moment at least, comes from firewalls and intrusion detection systems. That telemetry is changing a little bit more towards the endpoint, but we're not at that point yet that we would say every organization primarily relies on endpoint monitoring. So most of the monitoring still happens from networked sources. One such device is the intrusion detection system, the IDS. And if you believe the marketing people, an IDS performs deep inspection on network packets. The difference between a router and an IDS is somewhat important. A router will only look at the IP addresses. That's its job. A firewall will look at additional components. What the IDS does is look all the way down, so all the way or up, depending on what direction, to the application layer. But then it's going to map or match those data elements it finds to signatures of known bad behavior. And that means that every network packet, packet by packet, is inspected as it flows over the network. In the architecture here, we can see that we start our traffic on the internet. It's then routed into our internal network, passes through a firewall, which hopefully keeps out a good part of the unwanted traffic, and then passes through a network where it's in the end routed on the internal network to the server that is going to meet its requests. In between the firewall and the router, so right immediately after the firewall, we can have an intrusion detection system that is keeping an eye on what is going on. In a sense, you might say that the intrusion detection system has two roles. One is to check for malicious behavior, but the other one is also to check that the firewall did its job correctly. Now notice how the routers and the firewalls are drawn in line with the traffic, while the IDS sits out of band. It's actually how most intrusion detection systems work. They get a copy of the network traffic, but not the actual network traffic itself. And that means that when an IDS triggers an alert, the traffic has already gone through, and so you're always looking at something that has happened in the past. That's one limitation of an intrusion detection system. The benefit, of course, is if there is a failure in the IDS, it's not going to prevent our organization from being able to execute its mission. But that's one. An IDS always alerts on events that have happened in the past. Now, granted, that past may have just been a millisecond ago, but it's still the network packet has gone through at that point. A typical rule might look similar to the one you see here. So, for example, we're going to alert on any TCP packet from anywhere to anywhere. So any source IP import to any destination IP and TCP port 80, and say if we see the string union select SQL injection, we're gonna trigger an alert. Actually, no, the message is union select SQL injection. What we're looking at is content union. Now, of course, that means that if we're emailing someone through a webmail type thing that runs on HTTP instead of HTTPS, which should not happen, but if it happens and we have the word union in there, it's going to trigger an alert, even though nothing bad is going on. And that immediately comes down to one of the other issues, other than an IDS always reports on things that have already happened. The part is that those rules are often too loose, which means that they trigger too easily. Rules are always a matter of tuning. On the one hand, you want to make sure that you catch all situations so that you're not missing important events, but by doing that, you might also get a lot of noise in with that. And an IDS typically says, well, noise is something we can deal with. We can look at too many alerts, because if we do our triage and our incident response process, we'll be able to eliminate a lot of the noise, but at least we'll have the true positive packets in there. As long as you're not dealing with active blocks, then that's fine. But once you start changing from an intrusion detection system to an intrusion prevention system, that becomes an issue. The difference between the two primarily is that an intrusion prevention system is an inline device. And that means that it has to make a decision about network traffic as it's coming into the intrusion prevention system, and then make a decision whether or not to pass it through. It means it's triggering in real time, because when the trigger decides, no, we're not going to go through, the traffic is not going to go through. So in that aspect, it's very similar to a firewall. The firewall will only let traffic through if it matches certain patterns. The IPS will block traffic if it matches certain patterns. But because it's inline and it's actually looking at the actual traffic rather than at a copy of it, it can influence whether or not that network traffic goes through. False positives, though, become a problem, because now every time that I have a false positive, I have noise, I'm going to be blocking traffic that would have been legitimate. And if I run a business, for example, that relies on my online presence, that's a real issue. So in an IPS, the intrusion prevention system, the quality of the rules is going to be a lot more important. In practice, you see a combination of both fairly often, where I have the firewall as my first line of defense, the intrusion prevention system as my second line of defense, and then an intrusion detection system right after that as a third line of defense, and that ties in nicely with our defense in depth paradigm. I briefly mentioned this earlier when we were talking about the distinction between a firewall and a proxy, and that is the use of TLS. More and more network traffic is using TLS. At the moment, if I look at our live stats, I would say that probably close to 90% of all the network traffic, maybe even more than that at the moment, is TLS encrypted. And that means I can't look at it. Well, I can look at it, I don't know what it says. And that is a trend that will not revert. End-to-end encryption is becoming more and more important, but it also means that network-based intrusion detection and network-based intrusion prevention is becoming less and less effective. And so we have a couple of options there. One is to route it through proxies, but that's undesirable in many cases. The other one is to do all kinds of nasty networking tricks by doing on-the-fly TLS certificate rewriting, which is not a great practice to be in the first place. And then lastly is not to inspect traffic at all, at least not on the network. And that's kind of the direction we're going in. Of course, there will always be network traffic we need to inspect, but the traffic is not encrypted, by the time that it reaches the host. So maybe instead of being able to do everything nicely in this one central location in my network, I now have to start putting these sensors on the individual hosts that receive or send the encrypted traffic and look at it there. That's kind of the direction that stuff is moving in. I mentioned before that logs are very important. I can look at a network, but I only see what's happening there now. I don't see what has happened already, and I can't retain what's happening on a network. And so I need to rely on logs, records of activity. And when we're dealing with that, there's quite a few things that we need to get right. So first of all, logs take a lot of space, physical storage space, and that means they need to be stored somewhere. Depending on what kind of device you have, these logs are coming in at a ridiculous pace. We've seen situations where logs grow faster than we can look at them, even if we're running them through a tail session. And so that is by itself a computational challenge right there. How can I receive data fast enough and write it to disk in a way that I can actually still search it and alert on it? That also means that I can't keep them forever. And even if I can, I probably don't want to keep them forever. And so logs must be purged after a time. That, from a technical perspective, is not very difficult, but from a organizational perspective, where we have to have policies in place and we have to make sure that we comply with all of those policies, becomes pretty tricky. Now, logs can also be very structured, in which case the data structures are very clearly defined, and you know exactly what you're looking at. The Windows event logs are one example. Or they can be unstructured Linux logs, where every application kind of decides for its own what to write to a log file. One isn't necessarily better than the other, but they're very much different. There's also different ways to represent the same type of event. For example, I may have a login to an SSH service, I may have an authentication event, I may have a Windows login event. All three really represent the same thing. A user successfully authenticated to my infrastructure, but they look very different. And that means if I'm going to search through those logs for patterns, I have to be aware of that. Other logs contain very much the contextual information. So not such as, okay, this user logged in from that IP address, but this user with that user ID logged in from this IP address, where they were logged in from that IP address with that user ID, and lots of additional information. Well, those are typically the Windows logs, while Linux logs are typically very minimal. They list what they have to list, and that's it. If you need context, you have to look in the other logs yourself, which makes it harder to analyze them. Logs can contain sensitive data. People mistype their passwords into the login fields. So if you're gonna record, user learner failed login, or you might say user, secret password failed login, and immediately after that, from the same IP address, a user learner with a successful login, now you know what my password is. That's one example. There's many different types of sensitive data that could end up in those logs, so those logs really have to be protected very much. And logs don't happen spontaneously. Most systems must be configured and fine-tuned, ongoing, so too, to create those logs and to send them off to the right location. So maintaining logs for visibility is actually quite an extensive job. One type of special logs are NetFlow logs. NetFlows are network metadata. So for example, source and destination IP addresses, protocol, source and destination ports, if the protocol, the transport layer lets that, start time, end time. So there's only really a handful of data points, but for every single conversation happening, we could be writing those net flows to disk. And this could be very useful to do something called network traffic analysis. In network traffic analysis, we're looking for patterns. We're looking for deviations from the norm. We're looking for maybe a correlation with, hey, we know that a particular IP address and port number combination is used to send malware. Can we see connections to those networks and IP addresses in our NetFlow logs? And if so, we know that we might have a problem. NetFlows are also used for operational reasons, troubleshooting, for example, and sometimes for billing, so that we bill the right customer for the right amount of data that they've been using. They're a very simple log. They tend to get very, very large though, but they can contain very useful information. Now, all of those logs and all of those problems can be collected by a SIEM, a Security Information Event Management System. And the idea of those SIEMs is that they take a lot of that work that requires thought and automate it. So the log collection part, the log normalization part, analysis, correlation, reporting, alerting, retention, and disposal, all of that stuff can typically be done through a SIEM. And that means that if you start collecting logs from all these different sources into a single SIEM, which then normalizes it so that all those login events can actually be recognized as login events, I might start seeing a sequence that a single failed login to a system, for example, isn't a reason for alert. But I've seen all my systems having a single failed login from the same IP address at the same time. Now it becomes something that's worth looking at. And a SIEM can help with that. For quite a while, SIEMs were really considered the state of the art. This is what everyone needs to have. It will solve all of your security problems. And of course, it's not true. It's just a tool. But it's a very useful tool. But it's also a tool that requires a lot of fine-tuning, a lot of operational effort, and a lot of storage space, as well as computational resources to do all the work. So it's not a cheap option. In addition to those network defenses that we've talked about so far, so those are the firewall of its different variations. We talked about proxies. We talked about SIEMs between and the NetFlow data that goes into that. Between those 3 or 4 defensive controls, you really have the most important one. Now, you can buy dozens and dozens more products that all claim to secure the network. However, each of those devices has a typical niche that they are good at. This is a thing that can be very well used for detecting phishing attacks, but it also means that they need to be located in the right place in our network architecture. It means that they have to be operated by an operator who knows what they're doing, configuration and maintenance. And so every time you add these controls, you're also adding overhead. You're adding complexity, you have the potential that you're increasing latency, and you're adding points of failure. And remember, all the way in the beginning, we said minimize your attack surface. So you're potentially opening up more vulnerabilities on your network by introducing newer devices. And at that point, you have to really make the determination, is adding more controls worth it to me? That determination depends on the circumstance you're in. Some of the more popular ones are DLP, data loss prevention. You can think of it as a reverse intrusion detection, where an IDS is typically concerned about traffic coming onto the network. DLP is interested in recognizing traffic leaving the network that shouldn't be leaving the network and alerting on that. So it's a good tool to detect data exfiltration. Network access control is all about preventing unauthorized devices from connecting to the network in the first place. So I might define a network access control policy that says, well, if you're not fully patched on a current operating system and your antivirus isn't running, then I won't even let you onto my network in the first place. That's something that NAC can do, network access control. And then lastly, I mentioned them briefly, email gateways that do inspection of email and email patterns, tagging them as like, oh, this is email coming in from an outside source. Be extra careful with it for phishing detection and all of those. There are many more technologies out there, but between the firewall, the proxy, between the SIEM and these 4 DLP, NAC, and email gateways, those are your primary traditional defensive network countermeasures.